Hello, in this video we are going to talk about the SDN control plane. You know that SDN stands for software defined networking. So historically in the internet, the concept was to distribute the information among the routers. So in the traditional IP routing, the router is a kind of monolithic device which contains switching hardware with proprietary implementations related to the operating systems. They can run different routing protocols or IP protocol or intra and inter-domain protocols, but in proprietary router operating systems like, for example, the Cisco ones, and also different functionalities in the network can be moved to different middle boxes to be run. For example, firewalls, load balancers, not a network address translation boxes. So the idea was to, the router has the power, the router has both the data plane and the control plane installed inside, and the information that is exchanged among routers can be done in a distributed way to compose a routing protocol. But since more or less 2005, the Internet Task Engineering Force started to think about the possibility of changing these types of functionality. For example, why we don't change the distributed paradigm by a centralized one where there is a logically centralized device with all the information in the network that can help to run the routing algorithm in an efficiently way. So just to remind you the difference between the traditional IP networks and the SDN networks. In the traditional IP networks, we have the control plane and the data plane inside the router. So we have the router, we have both planes inside the router. So remember that the data plane is related to the next process. If I'm a router, I receive an incoming packet from an incoming port. So I check the IP header and I decide which is the outgoing link based on the match with the forwarding table. So this forwarding table is local to the router and it belongs to the data plane. But in order to have these forwarding tables filled with information, we need to run a distributed routing algorithm. For example, the leak state Dijkstra algorithm or the distance vector algorithm based on the Bell-Montfort equation. So these algorithms in traditional IP routing are distributed among all the routers belonging to the network. They send messages to the neighbors and they can incrementally have the information about the whole network. The main difference with the novel SDN paradigm is that basically the most important difference is the separation between the control plane and the data plane. The switches, the devices are simpler, are faster than the traditional router in traditional IP routing, but the data plane is the same. The data plane is related to the, in this case, flow table, not forwarding table, flow table. So the same process, I receive a packet from an incoming port, I check my flow table, is there any match with the incoming packet, yes or no? But I need to have the information inside the flow table. And who is in charge of updating this information? The controller. This controller is, we can think on a single device, but if there is only one device, it's a single point of failure in the network. If it is working not in a proper way. We can have problems in the network if it is turned off or failing. The network is degrading, the performance is decreasing, and we can have problems. So also, we have an idea of having one single controller. In reality, we have a set of controllers that are distributed throughout the network, and they can share the information to have a single view of the whole network. So, coming back to the separation between the control plane and the data plane, maybe it's the most important feature of software-defined networking. Why a logically centralized control plane? So first of all, in order to have a centralized view of the network, it's easier to compute a routing algorithm. So it's easy to have network management to avoid router misconfigurations. For example, we have different information in the routers in traditional IP routing, and we have to be sure that if we are all in the same wavelength, if we have the same information to be able to run the routing algorithm. In the case of SDN, we all have the same picture of the network, and we can run the algorithm taking into account that all of us have the same information in the network. In the case of traditional IP routing, it is not sure because maybe I'm a router, you are another router, and I have a picture of the network that is different from yours. Obviously, we can run our asynchronous routing algorithm, but it's difficult to be handled. The generalized forwarding, you remember that we have different fields to create a match in a rule. It's called table-based forwarding. There is a protocol called OpenFlow with different types of messages to be exchanged between the switches and the controller. For example, the controller can say, can you give me the information about your traffic loading your links, or which is the occupation of your flow table, how many rules do you have? So in order to have these request reply actions, we need to run an OpenFlow, the OpenFlow protocol. So it's easier to create algorithms on top of the controller to basically feed the flow tables. So at the end, centralized programming is much easier than distributed programming because, as I previously mentioned, centralized programming, we have all the picture of the network, whereas in the distributed programming, we only have our local view because we are a router. And we need more messages in the distributed programming than in the case of a centralized, so it's easier for a programming router, let's say. And this OpenFlow protocol, it's open, so it was created in 2008. Nowadays, we are in the version 1.5, if I'm not wrong, and it's an open protocol that is growing thanks to the research community, and it's used for SDN. Now we can see an analogy in the process of migrating from traditional IP to SDN. As in the case of migrating from a mainframe to personal computers. If we think on the computers before PCs, we had a monolithic device in which the three layers called hardware, software in terms of operating systems, and software in terms of applications were all integrated in the same device, belonging to the same vendor. They were closed, that you had to buy everything belonging to the same vendor. So it was a slow innovation in a small industry, but with the migration from mainframes to PC, uh, we finally could have different hardware vendors, different operating systems like Windows OS, Linux or Mac OS, and on top, different applications running on each of the different operating systems. So we pass from a closed to, let's say, open computers. And in order to pass from the hardware layer to the operating system layer, we had an open interface. And in order to pass from the operating system layer to the application layer, we also have open interfaces. So it's the same that in the case of SDN. We move from routers in which the data plane and the control plane were all included inside the router to SDN in which both planes are separated. Data plane is in charge of simple devices, switches, and the control plane is managed by a powerful entity called the controller. In the next slides, I want to share with you some questions about traffic engineering. Traffic engineering is the method. It's not a method. It's a research field in which network operators think about how to run, how to propose routing algorithms in order to improve the network performance according to some metrics. For example, I want to propose an algorithm for routing, taking into account that I want to use the less number of hops between the source and the destination, or the in order to save energy, I want to use the least number of links in order to power them off. So depending on the metric, I can create different algorithms in the controller. So in traditional IP, traffic engineering was very, very difficult. I want to share with you a picture of a network, this network, with a set of nodes connected by a set of links with a different costs. And I want to ask you a question. What if network operator wants to send the traffic from U to Z by means of the path UV, VW, WZ, and then he or she also wants to send the traffic from X to Z by means of this flow X, W, WY, YZ. First question, is it possible to do this with traditional IP routing? Yes, no, and why? Second scenario, in this case, we want to split the traffic being sent from U to the rest of the node and divide the traffic in 50%, 50%, 50% going from U to W, 50% from U to X. Next question. Is it possible to do this? Is it possible to do load balancing? Yes, no, and why? In traditional IP routing, I mean. In this slide, we have this scenario of the first question. We wanted to send the traffic from U to Z by using the path that is represented by red, and the traffic from X to Z by using the path represented by blue. So the critical point here is the node W. What if W wants to route the blue and red traffic in this way? The red traffic using this link and the blue traffic using this link. Is it possible to do it on a traditional IP routing? Yes, no, and why? And how to do it using SDN? Um, in the next, I want to share with you the four main parts of the software-defined networking paradigm. The first one is the concept of generalized forwarding. So the difference between traditional IP and SDN in terms of forwarding basically is that in traditional IP routing, we only care about the destination IP address. In the case of generalized forwarding and SDN, we can combine different fields from different headers, from different layers to compose the match. Another difference is that in the flow table of an SDN node, we have a column called counters to record the number of packets, the number of bytes that had a match with a specific rule. This way we can have more information if we are the controller to update our routing algorithm. So this is the first point. The second point, as you may know, is the separation between the control plane and the data plane. We all know this separation in SDN. So data plane, different devices, simplest, fastest devices compared with traditional routers, and the control logic is in charge of the centralized controller. So these functions from the control player run on the controller, and there is an interaction between this information it has about the network and the different applications that can be run on top of the controller. I want to share with you different types of applications. We have been talking about routing applications. For example, we want to apply the Dijkstra link state routing algorithm, taking into account all the information we know from the network. Another different application can be an access control list, ACL, in order to block all the traffic that we don't want to accept in our domain. Imagine we have different SDN nodes at the edge of the network of the domain. We want to block a specific packets coming from specific networks. So we can run an algorithm on top of the controller to do this. Another different application, load balance application. For example, we want to have all the links with the same traffic load or similar traffic load. Instead of having a subset of links with 100% of traffic load or approaching to 100%, and the rest of the links that are underutilized. So maybe we want to have 50% of traffic load in all the links instead of having a subset of them with a big traffic and the rest with low traffic. So the idea is to have all of them with the same average traffic. So this separation between the data plane and the control plane is done in this way by means of a southbound API, where the data plane can communicate with the controller using the OpenFlow protocol. So the first layer is the data plane. Fast, simple commodity switches implementing the generalized forwarding. They can communicate with the controller by means of the OpenFlow protocol, which is basically open and not proprietary. If we move toward the SDN controller, first of all, we have the network operating system. We have to select a specific controller. We will see different types of controllers. The controller operates with the data plane by means of southbound API, and with the applications by means of a northbound API. So on top of the controller, we have the specific applications like the routing, access control list, or load balancing that I have previously mentioned, and they are the brain of the network. So the network operator can add different applications or modify different applications according to their necessity. Which are the components of an SDN controller? So here we have the data plane. On top we have the different applications. We're going to learn how a controller is composed of a communication layer. So we need to use a protocol to communicate the controller with the devices. Basically, it's open flow. Then we have a middle part, a middle manager, to have information about the links states, the hosts, the switches, in order to retrieve statistics, and also have information about the content of the flow tables, which is the remaining space they have. So this layer is called network-wide state management layer. And on top of this second layer, we have an interface, an API, to communicate the controller with the applications. Here we have a global view of the network with the network graph. We can use RESTful APIs or intents to communicate with the applications. The OpenFlow protocol is the communication protocol that is able to communicate the controller with the switches. So we normally represent this picture. We have the centralized controller, we have the network graph, and there is a link connecting each switch, each node with the controller. Normally, it is used TCP protocol to exchange messages, and we have an optional encryption. So there are three types of messages. The first one is the message that is sent from the controller to the switch in order, for example, to request some information about the links, the port status, the status of the switch in general. Another type of message is a message that is sent from the switch to the controller. For example, after a request from the controller, I can give you the information. Or if there is a warning because the controller said, okay, notify me if you exceed an 80% of link load on any of your links. So if this happens, the switch will send a synchronous message to the controller in order to say, okay, I have exceeded this value. And the third type of message is a symmetric one. It's a kind of hybrid message that is sent from the controller to the switch and from the switch to the controller. Let's start with the messages sent from the controller to the switch. First of all, so the flow is from the controller to the switch. First of all, we can have a message to ask for the features of the switch. So, for example, how many ports do you have? Which is the type of the links do you have? So, information about the switch. Another type of message is the controller, the configure OpenFlow message that queries set switch configuration parameters. For example, you have to modify this parameter on this port because I think it's better to run at this bandwidth. For example, if we have a line card with different possibilities on bandwidth rate, to configure different objects in the queried switches. A third message is the modify state in order to add, remove, or modify flow entries in the OpenFlow tables. And finally, the fourth message is the packet out message. The packet out is a response of a packet in. For example, imagine that this switch sends a packet in message to the controller because it doesn't know what to do with a specific packet. So the controller will answer with a packet out response. You have to add this rule in order to handle this type of packets. And in the future, you will know what to do with this type of packets because you already have a rule installed on your flow table. The other type of message from switch to the controller, we have the packet in that we have previously mentioned, the flow remove, because, for example, a rule has been expired because of a timeout. Each rule is installed with a timeout. If no packets match it, the rule for a period of time defined by the timeout, it is removed and the switch will advise the controller. And there is another type of message called port status to inform of a change on a port. We are going to see an example of the flow after a modification on a port status. Imagine there is a problem with this link on switch 1. So the first action is to notify the controller by means of the port status message that we have seen in the previous slide. Secondly, the SDN controller receives this OpenFlow protocol and updates the link state information on router on switch S1. Then the Dijkstra algorithm, which has a different view of the network, is able to run the link state routing algorithm, and with the outcomes of the result of the invocation of the routing algorithm, it can modify the routing tables, and finally the controller will tell the switches that are involved in this modification that they have to install different rules because of the link failure of the red link. Step 4 is the Dijkstra computation. Step 5 is the interaction between routing, the Dijkstra routing action and the flow tables, and action 6 is the notification to the different involved switches. Finally, we should talk about controllers. We have different types of controllers with different types of programming languages, different functionalities. I want to show you a couple of them. OpenDaylight controller, where we have the separation from the control plane and from the applications on top of it. At the end, we have the OpenFlow protocol, different managers for topologies, switches, and so on and so forth. And finally, on top of it, an API to communicate with the applications. Another type of controller, owner's controllers, the same. In this case, we have these added functionalities connecting with the data plane. We have info about the network, the nodes, the link, the host, everything. And on top of it, the app is to communicate with the control applications. In order to finish, I want to comment some challenges, especially from the migration from IP to SDN. So obviously, it's not easy to migrate a company or a ISP network from IP to SDN because the cost is critical. If I have 100 or 1,000 of nodes, it's not possible to migrate all of that at the same day. In only one day. So the idea is to do a transition from IP to SDN, selecting the best candidates to be migrated to capable SDN nodes. And it is one of the main challenges nowadays. The future is SDN, but we have to still work with IP. And as you may notice, I'm actually working on SDN in research activities. So if you want to work with SDN in your final project or in other scope, just text me and I will be glad to work with you. Bye-bye.